All right, you guys, let's continue our discussion on logarithmic functions. Now we're going to be looking at the graphs of our logarithmic functions. Okay, so it says because exponential functions and logarithmic functions are inverses of each other, the graph of the logarithmic function y equals log base a of x is the reflection about the line of y equals x of the graph of the exponential function y equals a to the x, as shown in this figure. Okay, so remember, we had two types of exponential functions. Okay, we had a growth model and we also had a decay model. Okay, this one on the right, okay, this would be our growth. Okay, if we're looking at our exponential, because remember, growth means that it's increasing from left to right. And on the left-hand side, this would be our decay exponential function, all right, because our exponential function is decreasing from left to right. Okay. Now, paired up on each one of these graphs is the inverse logarithmic function, okay? So for our growth graph, okay, we can see that as our exponential function is increasing, okay, so is our logarithmic function. And we will also see that they are symmetric, okay, across the line y equals x, okay? They are reflections of each other, mirrored images, okay? The same thing is true for the decay exponential function, okay? Both it and its inverse, okay, are reflective about the line y equals x. They are mirrored images, okay? All right, so let's dive a little deeper into their properties. All right, so the first logarithmic graph that we're going to look at is for a logarithmic function who has a base that's greater than 0, okay? So the domain for this function is from 0 to positive infinity. The range is all real numbers. This graph has x-intercepts. It has 1 at 1, 0. It has no y-intercepts, okay? And it has a vertical asymptote, which is the y-axis, okay? Then the graph of f contains the points 1, 0, a1, and 1 over a, negative 1, okay? And a logarithmic function is decreasing if its base is from 0 to 1, in between there, and it's increasing if its base is greater than 1, okay? So this would be the case where it's increasing, okay? We're looking at the pink graph for the logarithmic, and this would be the case where the function is decreasing when we're talking about the logarithmic, okay? So you'll notice that both of these logarithmic graphs, so the pink graphs, they have vertical asymptotes, okay? That vertical asymptote is the y-axis, okay? You'll see that the pink graphs do not cross over the y-axis, okay? So that's reversed because remember, our exponential functions had horizontal asymptotes, so everything is reversed for our logarithmic functions, okay? And you'll also notice that these graphs are smooth and continuous, okay? Now I've kind of put together a table for us so we compare the differences between our exponential function and our logarithmic function, okay? So our exponential functions had y-intercepts, okay? But our logarithmic functions have x-intercepts, okay? And you'll notice that because they're inverses of each other, these coordinates just switch positions, okay? Because the domain and the ranges have flip-flop between the function and its inverse, okay? You'll notice that the domain for the exponential is all real numbers, negative infinity to infinity, whereas that's the same thing as the range for the logarithmic function. And you notice that on the range for the exponential, it's positive, so it's from 0 to positive infinity, and that's the same thing as the domain for the logarithmic, okay? Exponential functions have horizontal asymptotes, and logarithmic functions have vertical asymptotes. Okay, so just notice once you know the properties of one, it's the reverse for the other one because the exponential function and the logarithmic function are inverses. Okay. All right, let's talk about the natural log. Okay, so it says if the base of a logarithmic function is the number e, the result is the natural logarithmic function. This function occurs so frequently in applications that it is given a special symbol. So we'll see ln. Okay, so we'll have y equals ln x if and only if x equals y to the e power. Okay, So usually we're used to our logarithmic functions looking something like this. Log base a of x, okay? So they're saying we will have the natural log if the base is e, okay? So rarely ever will you ever see this, log base e, or logi, okay? You will see this instead, natural log of x, okay? So ln replaces log base e. That is the notation. So anytime you see ln x, this is its equivalent, okay? So be careful for that. All right, so on this picture, you will see the exponential function with a base of e, and you will also see the equivalent natural log of x graph side by side. Because they are inverses, remember they're going to be reflective across the line y equals x. Okay. All right, now we have two popular logs, okay, we can call them that. We have the common log and we also have the natural log, okay? So if ever you are told to use the common log, okay, the common log is a log that has a base of 10, okay? So we write our logs, log base a of x. Rarely ever will you see log base 10 of x. If the base is 10, it's understood, so we write just log of x. So if you don't actually see a number here in the base position, it's actually understood to be 10, and it's the common log, okay? So f of x equals log of x. And then we also have the natural log, which we just went over. You will rarely see log base e of x. You will see ln of x, okay? Now, these are the only two buttons that you actually have on your graphing calculator, okay? So you actually have a button that says natural log, okay? And you actually have a button that says common log, okay? So when you see those buttons on your calculator, that is how you will access either the common log or the natural log. Cool?